Astronomers have found a planet orbiting the closest star beyond our Sun. It is roughly Earth sized. It sits in the region where temperatures could theoretically allow liquid water, and after years of studying it, we are left with a strange conclusion. Mars may be the better place for humans to survive. That sounds almost absurd. Mars is a frozen desert with an atmosphere far too thin to breathe, brutal radiation at the surface, and temperatures that can plunge below minus 200 degrees Fahrenheit. But Mars has one enormous advantage. We can actually get there. Proxima b lies more than 25 trillion miles away, orbiting Proxima Centauri, our nearest stellar neighbor. Even though that is practically next door on a galactic scale, reaching it with anything resembling today's spacecraft would take thousands of years. Distance, however, may not be its greatest problem. Proxima Centauri is a red dwarf, a small star capable of producing violent stellar flares, and Proxima b orbits incredibly close to it. So the same proximity that places this planet inside the so-called habitable zone may also expose it to conditions very different from anything Earth experiences. That raises an uncomfortable problem with one of astronomy's most familiar ideas. A planet can be the right size, it can orbit at the right distance, it can sit perfectly inside the habitable zone, and it can still be an extraordinarily hostile place. Mars has already shown us exactly how dangerous another world can be. Proxima b forces us to confront something harder. We barely know what is waiting there at all. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe and we'll be here whenever you need a quiet journey through the cosmos. Let's start with the two words that made Proxima b sound far more welcoming than it may actually be: habitable zone. For most of human history, the planets around other stars existed only as possibilities. Astronomers could map distant galaxies and measure the chemistry of stars, yet they had no confirmed world beyond our solar system. That changed in 1992 when astronomers Alexander Wolszczyn and Dale Frail announced planets orbiting the pulsar known as PSRB 1257 plus 12. Suddenly, planets were no longer something our sun happened to possess. They were part of a much larger cosmic population. The search soon narrowed toward a more difficult prize. Astronomers wanted rocky worlds where familiar chemistry might function. One useful guide became the habitable zone, the region around a star where temperatures could allow liquid water on a planet's surface, assuming suitable atmospheric conditions. Water matters because terrestrial biology depends upon it. It dissolves substances, transports nutrients, supports chemical reactions, and gives complex molecules an environment where biological processes can unfold. Every known organism requires it somehow, so when we search for life elsewhere, liquid water provides a sensible starting point. Then the number of known worlds began climbing rapidly. The National Aeronautics and Space Administration launched the Kepler Space Telescope in 2009. Rather than examining one promising star at a time, Kepler monitored vast numbers of stars for tiny decreases in brightness caused when planets crossed their faces. Before its retirement in 2018, the mission had confirmed more than 2,600 planets. That census transformed astronomy. Planets appeared around stars of different sizes, ages, and temperatures. Some systems contained tightly packed families, unlike anything surrounding our Sun. Others offered worlds roughly comparable to Earth in size. The galaxy increasingly looked like a place where planets were ordinary. Against that background, the announcement of Proxima b in 2016 carried unusual weight. Researchers using instruments at the European Southern Observatory had detected a world around Proxima Centauri the nearest star beyond our Sun. Its minimum mass suggested something broadly terrestrial, while its orbit placed it within the star's traditional habitable zone. You can understand why the discovery traveled so quickly. Here was a nearby planet, satisfying several criteria astronomers had spent decades searching for, yet researchers were careful with what those criteria actually proved. A planet can occupy a habitable zone without being habitable. The definition says nothing by itself about breathable air, oceans, radiation exposure, magnetic protection, surface pressure, or biological compatibility. This is where the phrase Earth-like becomes troublesome. It can describe one similarity while implying many others. A world comparable to Earth in mass or temperature may still possess conditions utterly hostile to us. Mars gives us a useful contrast. We know its hazards with extraordinary precision because spacecraft have studied it for decades. It remains hostile, yet reachable with technologies already under development. Proxima b represents something different, a promising astronomical measurement separated from us by immense uncertainty. That distinction changes what a second Earth really means. A red dwarf can remain alive for trillions of years. That extraordinary longevity sounds favorable until you consider how such stars behave. Proxima Centauri belongs to this family, formally classified as an M-type star. Red dwarfs are the smallest ordinary stars and account for roughly 70% of the stellar population in the Milky Way. Proxima Centauri is dramatically cooler than our Sun. Its visible surface is roughly 5,500 degrees Fahrenheit, while the Sun's reaches around 10,000 degrees Fahrenheit. It also produces far less total light. For a planet to receive substantial warmth, it must therefore remain extremely close. Proxima b does exactly that. One complete orbit takes only about 11.2 Earth days. From that distance, the star dominates its environment in ways our familiar sunlight does not prepare us for. Red dwarfs possess powerful magnetic fields. Their surfaces contain electrically charged plasma, threaded by magnetic structures that can twist, stretch, and suddenly reconnect. When that stored magnetic energy is released, the star produces a stellar flare, an eruption capable of sending intense electromagnetic radiation outward within moments. Ultraviolet radiation and X rays can arrive first. Streams of energetic particles may follow. Proxima Centauri produces these events frequently, exposing nearby planets to a much harsher radiation environment than Earth normally experiences. One event revealed how extreme that activity could become. On March 24th, 2017, the Atacama Large Millimeter and Submillimeter Array in Chile detected an enormous flare from Proxima Centauri. At its peak, the star became roughly 1,000 times brighter than its normal emission at the wavelengths being observed. The strongest portion lasted only seconds. That brief duration matters. Stellar radiation can change dramatically before a nearby planetary environment has any opportunity to respond. Proxima b sits close enough that these outbursts deliver intense energy across a comparatively small orbital distance. Our own Sun also flares. In September 1859, an immense solar eruption associated with the Carrington event struck Earth's magnetic environment. Telegraph equipment failed across parts of North America and Europe. Some operators reportedly experienced electrical shocks, while auroras appeared unusually far from the polar regions. Yet Earth orbits about 93 million miles from the Sun. Distance weakens the radiation and particle environment reaching us, while powerful planetary defenses further reduce exposure. Major solar storms of Carrington scale are also exceptional events, rather than the ordinary background of our star. Around Proxima Centauri, the balance changes. A planet receiving enough stellar energy for potentially temperate conditions must remain close to a magnetically active red dwarf. The same proximity that provides warmth also increases exposure. So when we picture Proxima b beside its faint reddish star, distance becomes strangely double edged. Move farther away, and the planet freezes. Remain close enough for warmth, and the star itself becomes one of the greatest obstacles to survival. Earth survives inside an invisible structure extending far beyond the atmosphere. Its magnetic field redirects many charged particles arriving from the sun, guiding some toward the polar regions. There, their collisions with atmospheric gases create auroras. Without that protection, the same particles could interact far more directly with the atmosphere. For Proxima b, that protection remains unknown. We have no measurement confirming whether the planet possesses a global magnetic field. Some models allow one under favorable interior conditions, while others produce much weaker protection. Either possibility matters because Proxima Centauri delivers an unusually aggressive stream of radiation and particles. The atmosphere would face the first prolonged assault. Extreme ultraviolet radiation and X rays can heat gases high above a planet's surface. Molecules become ionized, meaning electrons are stripped away. Once energized, atmospheric particles can escape into space or be swept away by the stellar wind. Over immense periods, this atmospheric erosion can transform the conditions below. Mars gives us a nearby example of the process. Its global magnetic field disappeared billions of years ago. Solar particles then interacted more freely with the upper atmosphere, gradually helping remove gases into space. Measurements from the National Aeronautics and Space Administration's Mars Atmosphere and Volatile Evolution mission have directly observed this continuing loss. Yet Mars receives that punishment from our comparatively restrained Sun. Proxima b occupies a harsher stellar environment. Atmospheric models have therefore produced troubling outcomes. Under strong stellar wind and high energy radiation, an Earth like atmosphere could lose substantial quantities of gas over hundreds of millions of years. Although the exact rate depends heavily on magnetic protection, atmospheric chemistry, and replenishment from the planet itself. Any surviving atmosphere would still need to protect the surface. Ultraviolet radiation can damage biological molecules, including deoxyribonucleic acid. Earth limits much of that exposure through ozone, a form of oxygen concentrated in the upper atmosphere. Ozone absorbs dangerous ultraviolet wavelengths before they reach us. Repeated powerful flares complicate that defense around an active red dwarf. Energetic radiation can alter atmospheric chemistry and reduce ozone concentrations. Some simulations find severe depletion after repeated events, leaving surface organisms exposed to radiation far beyond normal terrestrial conditions. Recovery depends on the atmosphere, flare frequency, and chemical environment. This is where Mars offers an engineering advantage. Its radiation environment is dangerous, but we have measured it directly. Future crews can place habitats beneath Martian soil, use water and structural materials as shielding, or build inside natural underground formations. Surface activity can also be planned around measured radiation conditions. With Proxima b, we cannot yet design around a known radiation environment. We do not know the atmosphere, magnetic field, surface pressure, or shielding available there. A flare, therefore, becomes more than a burst of stellar energy. Repeated across geological time, it can reshape the entire boundary between a planet and space. Imagine standing where daylight never advances across the ground. Ahead, Proxima Centauri remains fixed in the sky. Behind you lies a hemisphere where the star never rises. If Proxima b behaves as many orbital models predict, Sunrise and sunset may have little meaning across most of its surface. The cause is tidal locking. Gravity does more than keep a planet in orbit. When a nearby star pulls unevenly across a planet, repeated gravitational flexing gradually changes its rotation. Over immense spans of time, that rotation can slow until one spin takes exactly as long as one orbit. Proxima b completes its orbit in roughly 11.2 Earth days. If fully synchronized, its rotation would take the same amount of time. One hemisphere would continually face Proxima Centauri, while the opposite hemisphere would remain turned away. That creates an unusual climate problem. Stellar energy continually reaches the day side, while the night side receives none directly. Without substantial atmospheric circulation, temperatures between these regions could diverge dramatically. Some models allow intense dayside heating, while exposed nightside regions could fall below minus 220 degrees Fahrenheit. Between them lies the terminator, the boundary separating permanent daylight from permanent darkness. On a tidally locked world, this boundary could remain geographically fixed. Researchers have explored whether a temperate belt might exist there, creating a narrow region where conditions fall between the two extremes. But temperature alone cannot make that region livable. A substantial atmosphere could redistribute heat through powerful winds. Oceans, if present, could transport additional energy through currents. Climate simulations show that some tidally locked planets might avoid extreme temperature differences if their atmospheres remain thick enough. With sufficient circulation, heat from the day side could reach the night side and prevent atmospheric gases from freezing onto the surface. For Proxima b, every part of that scenario depends upon properties we cannot yet measure. Atmospheric pressure remains unknown. Oceans remain unconfirmed. Even the planet's exact rotational state has never been observed directly. Its rotation may also influence magnetic protection, although the relationship is more complicated than rotation alone. Planetary magnetic fields arise from moving electrically conductive material inside their interiors. Rotation can help organize that dynamo, but interior composition, heat flow, and convection also matter. A slowly rotating planet could therefore retain a magnetic field under certain conditions. Mars offers a very different rhythm. One Martian day lasts about 24 hours and 37 minutes. Sunlight crosses its landscape, nights follow days, and seasons develop as Mars travels around the Sun. For human biology, that familiar cycle matters. Sleep, hormone production, metabolism, and alertness all respond to recurring patterns of light. On Proxima b, a settlement might instead exist beneath a star fixed permanently above one horizon, living within a planetary clock unlike anything our species evolved to experience. Every breath you take depends on an unusually precise planetary arrangement. At sea level, Earth's atmosphere presses against us at roughly 14.7 pounds per square inch. About 78% is nitrogen, 21% is oxygen, with the remainder composed of argon, carbon dioxide, and other trace gases. That mixture supports respiration while helping regulate the planet's climate. Pressure matters just as much as composition. Human lungs evolved to exchange gases within a particular range of atmospheric pressures. Oxygen alone does not guarantee survival. A planet could contain familiar gases and still leave an unprotected person unable to breathe. Earth's atmosphere performs other work as well. Greenhouse gases retain enough heat to moderate temperatures, while ozone absorbs much of the harmful ultraviolet radiation arriving from the sun. We live beneath several interacting layers of protection. For Proxima b, None of those details has been measured directly. We cannot currently determine whether it possesses a substantial atmosphere at all. Researchers instead construct models using the planet's orbit, estimated mass, and the observed behavior of Proxima Centauri. Those simulations explore how different atmospheres might survive across billions of years. A study published in the Astrophysical Journal Letters in 2017 examined atmospheric escape under the intense radiation environment surrounding Proxima Centauri. The results showed that atmospheric loss could be severe, particularly when stellar radiation and charged particles repeatedly energize gases high above the surface. Even retention would solve only part of the problem. Composition matters enormously. An atmosphere dominated by carbon dioxide would be poisonous to humans. Nitrogen, without sufficient oxygen, could not sustain respiration. Pressure, chemistry, temperature, and radiation protection would all need compatible values before an exposed human body could survive. Mars gives engineers something far more concrete. Its atmosphere has roughly 0.6% of Earth's sea level pressure. Carbon dioxide makes up about 95%, followed by nitrogen and argon in much smaller amounts. Humans cannot breathe it, yet spacecraft have measured its composition, pressure changes, seasonal behavior, and interactions with the surface. That knowledge creates possibilities. In 2021, the Mars Oxygen In Situ Resource Utilization experiment aboard the Perseverance rover successfully produced oxygen from Martian carbon dioxide. The device separated oxygen atoms from carbon dioxide molecules, demonstrating that useful resources can be extracted directly from the surrounding atmosphere. Mars still requires sealed habitats. Its surface pressure is so low that stable liquid water generally cannot persist there under ordinary surface conditions. Humans would need controlled pressure, oxygen supplies, and extensive life support. But those requirements can be designed around measured conditions. We know what gases enter an intake, what pressure surrounds a habitat, and what equipment must compensate. With Proxima b, even that first engineering specification remains blank. Before asking whether we could breathe its air, astronomy must establish whether there is meaningful air to breathe. 4.2. 4 light years looks modest on an astronomical chart. For a spacecraft, it becomes almost 25 trillion miles of empty space. Light itself, moving at roughly 186,000 miles per second, needs 4.24 years to cross that distance. Everything humans have built moves far more slowly. Consider the Parker Solar Probe. During its closest approaches to the Sun, gravity accelerates it to extraordinary speeds. By December 2024, it reached roughly 430,000 miles per hour, making it the fastest human-made object ever recorded. If a spacecraft could somehow maintain that speed toward Proxima Centauri without needing acceleration or braking, the journey would still last more than 6,000 years. Voyager 1 gives us another scale. Launched in 1977, it has traveled farther from Earth than any other spacecraft, reaching more than 15 billion miles away. That achievement spans generations of engineering and communication. Yet at Voyager 1's cruising speed, crossing the distance to Proxima Centauri would require tens of thousands of years. So speed becomes the central obstacle. In 2016, Stephen Hawking and Yuri Milner introduced Breakthrough Starshot, an initiative exploring tiny robotic spacecraft driven by powerful Earth-based lasers. The concept uses lightweight sails pushed by concentrated light, potentially accelerating miniature probes to around 20% of light speed. At that velocity, reaching the Alpha Centauri system could take roughly 20 years. Those machines would be tiny probes, however, not crewed vessels. A human spacecraft needs life support, shielding, power, supplies, structural mass, and eventually some way to slow down. Accelerating all that material to even 10% of light speed demands an extraordinary amount of energy. Relativity also makes every additional increase in velocity progressively more demanding. Distance creates another problem after arrival. Suppose you could stand on Proxima b and send Earth a message. Your transmission would travel at light speed, yet Earth would receive it more than 4 years later. A reply would require another 4 years. A simple exchange would span more than 8 years. Rescue would have no practical meaning. Neither would rapid resupply. An interstellar crew would function independently from Earth in a way no expedition in human history has experienced. Mars operates on another scale entirely. At favorable orbital positions, it can approach within roughly 34 million miles of Earth. Radio signals between the planets take several minutes at minimum and more than 20 minutes when geometry stretches the distance. That delay prevents ordinary conversation, but engineers can work with it. Commands can reach spacecraft within the same hour. Mission teams can respond to developing problems. Supplies can cross the distance within months. Proxima b turns distance itself into part of the survival system. Every kilogram, every replacement component, every medical resource, and every decision must account for a separation measured in years, even for light. Proxima b entered astronomy through a movement too small for human senses. No telescope captured a disk, coastline, cloud layer, or surface. Instead, astronomers watched Proxima Centauri itself and measured tiny changes in the star's motion. From those changes, the planet emerged mathematically. This technique is called the radial velocity method. An orbiting planet pulls gravitationally on its star, causing both bodies to move around their shared center of mass. From Earth, the star alternately shifts toward us and away. Those motions slightly change the wavelengths of its light through the Doppler effect. For Proxima Centauri, the pattern repeats every 11.2 days. The signal revealed Proxima b in 2016, and more precise observations confirmed it in 2020. Yet radial velocity measurements provide a surprisingly narrow collection of facts. We know the orbital period. We can estimate the planet's orbital distance. Modern measurements place its minimum mass at roughly 1.05 times Earth's mass. Beyond those properties, the picture becomes far less complete. Radial velocity gives only minimum mass because we do not know the exact inclination of the orbit relative to our line of sight. A tilted orbit would mean the planet is somewhat heavier than the minimum measurement suggests. Statistical and dynamical constraints favor a terrestrial scale, but mass alone cannot reveal whether the surface is rocky, ocean-covered, or shaped by some unfamiliar mixture of materials. We have never measured its radius. Without both radius and mass, astronomers cannot calculate its average density, one of the best clues to planetary composition. No confirmed transit crosses Proxima Centauri from our viewpoint, removing one of astronomy's most useful methods for measuring planetary size. Then there is the star itself. Proxima Centauri's activity produces changes in its spectrum that researchers must separate from genuine planetary motion. The confirmation work, published in 2020, specifically modeled this stellar activity while recovering the planetary signal with greater precision. The planet is considered firmly detected, but its host star makes every delicate measurement harder. Now, compare that uncertainty with Mars. Orbiters have photographed its terrain at scales fine enough to distinguish small surface features. Landers have touched its soil. Rovers have drilled rocks, sampled the atmosphere, recorded weather, and watched dust move across the ground. We know winter temperatures near the poles can fall toward minus 220 degrees Fahrenheit, while warmer equatorial afternoons can approach 70 degrees Fahrenheit. Water ice has been mapped, minerals have been identified, atmospheric behavior is monitored across seasons. Engineers can choose landing sites using actual terrain data. With Proxima b, we cannot yet choose a continent. We cannot confirm there are continents at all. The difference between these worlds, therefore, begins before any spacecraft launches. Mars presents known dangers in extraordinary detail. Proxima b remains largely a set of gravitational measurements, carrying an entire planet inside a handful of numbers. Radiation on Mars is dangerous in a useful scientific sense. We can measure it, map its sources, estimate its biological consequences, and design structures around it. That turns an invisible hazard into numbers engineers can actually use. The Curiosity rover carried the radiation assessment detector during its journey from Earth and continued measuring after landing in 2012. Results published in Science in 2013 revealed the radiation environment astronauts would encounter during interplanetary travel and on the Martian surface. Galactic cosmic rays are a major source. These are highly energetic particles arriving from beyond our solar system. Solar particle events add another hazard when eruptions from the Sun accelerate particles through space. Mars offers little natural protection from either source. Using Curiosity measurements, researchers estimated that a mission involving roughly 180 days traveling each way, combined with 500 days on Mars, could produce a total dose near 1 sievert. Actual exposure would vary with solar activity, spacecraft shielding, habitat design, and mission timing. That is substantial. The National Aeronautics and Space Administration currently limits an astronaut's total career effective dose from spaceflight radiation to 600 millisieverts, regardless of age or sex. A long Mars expedition could therefore exceed the entire career limit. But radiation risk does not mean immediate death. The primary concern at these mission doses is increased long-term disease risk, especially cancer. That distinction matters because exposure can be reduced. Mars itself provides shielding material. Several feet of Martian regolith, the broken rock and dust covering the surface, could absorb part of the incoming radiation. Habitats could be buried beneath excavated material or constructed against natural slopes. Water, food stores, and equipment can also be arranged around occupied spaces to add protection without requiring dedicated shielding mass everywhere. Lava tubes offer another possibility. These underground passages form when flowing lava develops a hardened roof while molten material drains away beneath it. Orbital observations have identified collapsed pits and volcanic terrain consistent with subsurface cavities on Mars, although the dimensions and accessibility of individual tubes still require direct exploration. A suitable cavern could provide thick natural shielding and more stable temperatures. Researchers are also investigating biological countermeasures. National Aeronautics and Space Administration studies have examined compounds intended to reduce radiation damage or its downstream effects in cells. Such treatments remain experimental, yet they add another layer to physical shielding and mission planning. Proxima b gives us no comparable radiation map. Its stellar environment includes intense X-rays, ultraviolet radiation, and energetic particle events whose surface effects depend on atmospheric and magnetic conditions we cannot measure directly. On Mars, you can assign radiation a dose, place limits around it, and add feet of shielding where people sleep. The hazard remains serious, but it belongs to engineering rather than speculation. Mars keeps much of its water hidden in ice. At both poles, layered deposits preserve enormous frozen reservoirs beneath seasonal coverings of carbon dioxide frost. The northern polar deposit alone contains enough water ice to cover the entire planet beneath roughly 36 feet of water if it were somehow melted and spread evenly. The poles are only part of the inventory. Radar and neutron measurements have revealed buried ice across broad regions, especially at middle and high latitudes. The shallow radar instrument aboard the Mars Reconnaissance Orbiter sends radio waves beneath the surface and records reflections from underground layers. Its observations have helped identify extensive deposits containing large quantities of water ice. Some lie beneath only a modest covering of soil. For future explorers, accessibility matters. Water extracted locally could supply drinking systems, agriculture, oxygen production, and rocket propellant. Instead of transporting every gallon from Earth, crews could mine frozen deposits, melt them, remove contaminants, and recycle the resulting water through closed life support systems. Far deeper beneath the southern polar region, radar produced a more mysterious signal. In 2018, scientists analyzing data from the Mars Advanced Radar for Subsurface and Ionosphere sounding instrument aboard the European Space Agency's Mars Express spacecraft reported an unusually reflective region roughly 12 miles across, buried about a mile beneath the ice. One interpretation was a reservoir of liquid water. Additional bright radar reflections reported in 2020 suggested several possible bodies nearby, yet their nature remains disputed. Later studies showed that certain minerals, clays, or unusual frozen materials might create similar radar signatures without requiring liquid water. If liquid does exist there, dissolved salts could help explain its survival. Perchlorates are salts found in Martian soil that can lower water's freezing point substantially. Under sufficient pressure and favorable chemistry, salty water can remain liquid at temperatures where pure water freezes. Mars also preserves evidence of a wetter past directly in its landscape. Ancient valleys branch across the highlands. Deltas contain layered sediments deposited by flowing water. Clay minerals and other altered rocks record prolonged interaction between liquid water and the Martian crust. Between roughly 4 billion and 3.5 billion years ago, rivers crossed portions of the surface, lakes occupied craters, and groundwater moved through rock. How long those conditions persisted varies by region, but water repeatedly shaped ancient Mars. That history gives us something practical today. We know where many frozen reservoirs lie. Orbital instruments can estimate their depth and extent. Engineers can evaluate landing regions partly according to nearby water resources. For Proxima b, no comparable inventory exists. We cannot confirm oceans, glaciers, vapor, or buried ice. Whatever water form there may remain, or stellar activity may have removed much of it long ago. Mars offers frozen water we can locate and eventually drill into. On Mars, your body would become lighter the moment you arrived. A person weighing 180 pounds on Earth would weigh about 68 pounds there. The person's mass would remain unchanged, but Martian gravity pulls with only about 38% of Earth's surface strength. That difference reaches far beyond easier walking. Human bones continually remodel themselves in response to mechanical loading. Muscles also maintain strength partly because gravity demands constant work. Reduce that load for long periods, and both systems begin adapting. We have seen the extreme version in orbit. Astronauts living aboard the International Space Station experience microgravity, where normal weight bearing nearly disappears. Despite daily exercise, they can lose bone mineral, muscle strength, and cardiovascular conditioning. Body fluids also shift toward the head, contributing to changes in vision and pressure within the body. After missions lasting around 6 months, returning astronauts may need weeks or months of rehabilitation. Standing, walking, and maintaining balance can require readjustment as the cardiovascular and nervous systems reacquaint themselves with Earth's gravity. Mars would provide more loading than orbital flight. Its 38% gravity should reduce some effects of microgravity, yet nobody knows how much protection that provides over years or decades. No human has lived continuously in partial gravity. Even the longest lunar visits lasted only days, far too briefly to reveal the consequences of years under reduced gravitational loading. That leaves important biological questions unanswered. Would bone loss eventually stabilize? Could muscles maintain healthy strength with exercise? How would pregnancy develop? Would children growing under weaker gravity form normal skeletons, hearts, and balance systems? We have no human data that can settle those questions. Researchers are testing ways to reduce the uncertainty. The National Aeronautics and Space Administration studies resistance exercise, nutrition, cardiovascular conditioning, and other countermeasures for long missions. Artificial gravity is another possibility. Long transit missions could use rotation to restore loading before crews ever reach the Martian surface. A rotating spacecraft or habitat can create apparent gravity by continuously pushing occupants toward its outer wall. Proxima b presents the opposite problem. We cannot calculate its surface gravity precisely. Radial velocity measurements provide a minimum planetary mass, currently estimated near Earth's mass, but its radius remains unknown. Surface gravity depends on both mass and radius. A compact, dense world could pull considerably harder than expected. For you, stronger gravity would affect every movement. The heart would work harder to move blood upward. Equipment would become more difficult to carry. Habitat structures would support greater loads, while falls and physical labor would impose additional stresses. Mars gives human physiology an unanswered experiment at 38% gravity. Proxima b gives us an unanswered value. Even an Earth-like result there would solve only one requirement among many, because comfortable gravity cannot compensate for an environment that remains biologically inaccessible. Temperature on Mars can change by more than 200 degrees Fahrenheit without moving very far across the planet. Near the poles during winter, readings can descend toward minus 220 degrees Fahrenheit. On a favorable summer afternoon near the equator, exposed ground can briefly approach 70 degrees Fahrenheit. The air provides little insulation. Mars has such a thin atmosphere that heat absorbed by the ground escapes rapidly after sunset. Daytime warmth, therefore, does not linger through the night as effectively as it does on Earth. For settlers, temperature control would become a continuous function of suits, habitats, power systems, and insulation. We already understand parts of that challenge. Antarctic research stations routinely operate through temperatures below minus 40 degrees Fahrenheit, with some interior regions falling below minus 70. Heated structures, layered insulation, redundant power, and specialized clothing allow people to work there for months. Mars adds lower pressure and greater isolation, yet extreme cold itself is an engineering problem with decades of terrestrial experience behind it. Dust changes the equation. Martian storms can expand across enormous regions, sometimes surrounding the entire planet. During the global storm of 2018, airborne dust dramatically reduced sunlight reaching the surface. The solar-powered Opportunity rover could no longer generate enough electricity to maintain normal operations. Its final communication arrived on June 10th, and repeated attempts to restore contact eventually failed. A settlement cannot depend on favorable skies. This is why nuclear fission has received serious attention for planetary surface power. The National Aeronautics and Space Administration and the United States Department of Energy successfully demonstrated the kilopower reactor using Stirling technology experiment in 2018. Compact fission systems could provide electricity through darkness, winter, and dust storms, keeping heaters and life support operating when solar output falls. Proxima b offers no equivalent temperature record. Any precise surface temperature depends heavily on an atmosphere we have never measured. A substantial atmosphere could circulate heat around the planet, reducing differences between illuminated and dark regions. Oceans could redistribute still more energy. A thin or absent atmosphere would allow far greater contrasts. That uncertainty makes dramatic estimates of scorching daysides and deeply frozen nightsides possible in some models, yet none can presently be treated as measured conditions. Even the boundary between permanent daylight and darkness becomes habitable only under particular assumptions about atmospheric pressure, winds, clouds, and heat transport. For a human body, the distinction matters. Exposure to either extreme can become fatal, but technology does not need pleasant outdoor temperatures to sustain life. It needs predictable thermal loads and dependable energy. On Mars, engineers can design heaters against recorded winter temperatures and cooling systems against known daytime peaks. They can test insulation against measured conditions. On Proxima b, we would first need to discover what temperature the habitat was being designed to survive. A future Martian greenhouse would begin with material that looks promising but is chemically difficult. Martian regolith contains several elements plants require, including nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. Yet having those ingredients present does not make the ground ready for farming. Their chemical forms, availability, and concentrations matter, while organic material is scarce. Perchlorates create a more immediate obstacle. These salts have been detected in Martian soil and can interfere with human thyroid function after sufficient exposure. They also complicate agriculture because crops could absorb contaminants through their roots. Before Martian regolith entered a food system, settlers would need to wash, chemically treat, or otherwise process it. Another approach avoids native soil altogether. Hydroponics could grow plants with roots suspended in controlled nutrient solutions. That gives engineers direct control over water, minerals, acidity, and contamination. We already have evidence that crops tolerate materials designed to resemble Martian ground. In 2016, researchers at Wageningen University reported successful growth of 10 crop species in simulated Martian and lunar soils, including tomatoes, peas, radishes, rye, and garden rocket. The experiment was encouraging, although the simulants did not reproduce every hazardous feature of actual Martian regolith, especially its perchlorate chemistry. Agriculture beyond Earth is also being developed much closer to home. Aboard the International Space Station, the vegetable production system and advanced plant habitat have supported experiments with lettuce, radishes, mustard greens, peppers, and other plants. Researchers study germination, root development, microbial behavior, nutrition, and crop health under unusual conditions. Each harvest adds practical knowledge to closed agricultural systems. Mars provides another useful resource directly overhead. Its atmosphere is dominated by carbon dioxide, the gas plants consume during photosynthesis. A pressurized greenhouse could therefore draw carbon dioxide from outside, process it, and maintain concentrations suited to crops. Water remains essential, but mapped ice deposits provide a physical resource that future settlements could extract, purify, and recycle. None of this makes Martian farming simple. You would still need dependable power, temperature control, artificial lighting when necessary, nutrient recycling, and protection from radiation. Crop failure inside an isolated settlement would carry consequences far beyond an ordinary failed harvest. But these are defined problems. We can build chambers, test crops, measure contaminants, and calculate resource requirements before people arrive. Try performing the same exercise for Proxima b. What soil would you design around? We have no sample, mineral survey, surface photograph, confirmed atmosphere, or confirmed reservoir of accessible water. We cannot determine whether its ground contains useful nutrients, toxic chemistry, or even conditions where conventional agriculture makes sense. Mars gives us imperfect materials with measurable properties. Proxima b gives us almost no agricultural data at all. One can support experiments today. The other remains beyond meaningful farming design. Every human settlement eventually becomes an energy system. On Mars, every breath, meal, warm room, radio transmission, and recycled gallon of water would depend on electricity. Fortunately, this is one problem we can already design around. Sunlight provides the most obvious source. Near the Martian equator, solar panels receive roughly 43% as much solar energy as comparable panels on Earth. That remains usable. Large arrays could power equipment during favorable conditions, while batteries store excess electricity. Dust changes the equation. Fine particles settle on panels, and prolonged storms can dramatically reduce incoming sunlight, making solar power alone an unreliable foundation for permanent settlement. Nuclear fission offers greater consistency. The National Aeronautics and Space Administration developed kilopower, a compact reactor concept intended for destinations including Mars. Its prototype used a uranium core and successfully completed ground testing in Nevada in 2018. Designs in the kilopower range could produce roughly 1 to 10 kilowatts of electrical power per reactor. Several reactors could operate together. A settlement demanding hundreds of kilowatts could expand its generating capacity by adding units as infrastructure grows. For a community approaching 1 megawatt of demand, many small reactors could provide redundancy. One failure would reduce capacity without disabling the entire colony. That electricity would immediately have somewhere to go. Heating, oxygen production, water processing, agriculture, communications, computing, workshops, and scientific equipment all require continuous power. Some minimal settlement studies place basic electrical demand around several kilowatts per person, though actual requirements would depend heavily on habitat design and industrial activity. Mars may eventually offer other sources. Geological observations indicate volcanism persisted surprisingly recently, perhaps within the last several tens of thousands of years. If accessible underground heat remains in suitable regions, future explorers could investigate geothermal power. We do not yet know whether practical reservoirs exist. Energy also connects directly to transportation. The Sabatier reaction combines carbon dioxide with hydrogen to produce methane and water. Since carbon dioxide dominates the Martian atmosphere, settlers could potentially manufacture methane locally after supplying hydrogen, perhaps obtained from water ice. That matters for spacecraft, using methane fuel. SpaceX designed the Raptor engine around methane and oxygen, while Starship mission concepts have long incorporated producing propellant from Martian resources. Instead of transporting every pound of return fuel from Earth, a sufficiently developed surface plant could manufacture part of what departing spacecraft need. Notice what makes these plans possible. We know the sunlight reaching Mars. We know its atmosphere contains carbon dioxide. We can map resources, test reactors, calculate electrical loads, and design machinery around measured conditions. For Proxima b, the energy spreadsheet begins mostly empty. Its surface environment remains unmeasured. We cannot plan around atmospheric resources, accessible fuels, geothermal reservoirs, or workable surface installations. Mars presents an enormous engineering challenge, but its power problem already has numbers, machines, and experiments attached to it. A voyage to Mars begins with timing. Earth and Mars are moving targets, circling the Sun at different speeds. Roughly every 26 months, their positions become favorable for an efficient departure. Miss that window, and the mission may wait more than 2 years. With current chemical propulsion, a typical journey would last around 7 to 9 months. That is long enough for the spacecraft itself to become an environment the crew must continuously manage. Space is limited. Privacy is scarce. The same small group works, eats, exercises, and sleeps within the same enclosed system for months. Communication also changes as Earth recedes. Depending on planetary positions, messages can require many minutes to cross the distance. Conversations become exchanges of recordings rather than immediate dialogue. Mission control can advise, but crews must increasingly solve urgent problems themselves. Researchers have studied this isolation directly. From 2010 to 2011, the Mars 500 experiment confined 6 men inside a simulated spacecraft complex near Moscow for 520 days. Researchers documented changes in sleep, activity, mood, stress, and social behavior. The experiment demonstrated that psychological performance can shift significantly during prolonged confinement, even when physical danger is simulated. The body faces another challenge. In microgravity, astronauts can lose roughly 1 to 2% of bone density per month in vulnerable skeletal regions. Muscles weaken as well. Crews aboard the International Space Station counter these effects with about 2 hours of daily exercise using resistance and cardiovascular equipment. Mars travelers would require similar routines throughout transit. Mission architecture has already been studied in remarkable detail. Conjunction class missions generally favor lower energy trajectories, transit periods of several months, and extended stays on Mars while planetary alignment cycles again. Opposition class missions shorten the overall expedition and surface stay, but require more demanding trajectories and greater energy. SpaceX has developed Starship around large payload capacity, orbital refueling, and eventual interplanetary transportation. Its upper stage stands roughly 170 feet tall in current configurations, with planned cargo capacity measured in well over 100 tons to low Earth orbit, depending on vehicle version and mission profile. Reaching Mars would require refueling after launch before committing to interplanetary flight. Even then, departure carries severe constraints. Early in some trajectories, contingency options may permit altered paths or eventual return. Farther along, turning directly around is not like reversing a vehicle. Orbital mechanics governs every maneuver, and rescue cannot simply be dispatched from Earth. Yet you can place all these difficulties inside mission models. We can calculate launch windows, food supplies, radiation exposure, exercise schedules, fuel requirements, and communication delays. Proxima b changes the scale completely. No presently demonstrated propulsion system could transport humans across more than 4 light-years within a human lifetime. Fusion propulsion remains experimental, while laser sail concepts are intended primarily for extremely small robotic probes. Mars demands extraordinary engineering. Proxima b demands capabilities humanity does not yet possess. In April 2016, an interstellar proposal moved from speculation into an organized research program. Physicist Stephen Hawking and investor Yuri Milner announced Breakthrough Starshot, with Mark Zuckerberg joining its board. The initial research commitment was $100 million. Its target was the Alpha Centauri system, our nearest neighboring stellar system, including Proxima Centauri. The proposed travelers would barely resemble spacecraft. Thousands of tiny probes, often called star chips, would weigh only a few ounces or less and carry miniature cameras, sensors, processors, and communication equipment. Each would attach to an extremely thin, reflective sail. Once deployed above Earth, an immense ground-based laser array would illuminate that sail and accelerate the probe rapidly. The intended speed is extraordinary, roughly 20% of light speed. At that velocity, a probe could cross the interstellar distance in about 20 years. Achieving it would require laser power on the scale of roughly 100 gigawatts during acceleration, alongside extraordinary precision. The beam would need to remain focused while pushing a tiny sail through space without destroying or destabilizing it. Then comes the material between stars. Interstellar space contains gas and microscopic dust. At 1/5 of light speed, even tiny particles become dangerous projectiles. Repeated impacts could erode a probe, damage instruments, or destroy electronics. Researchers have examined protective coatings, shielding geometries, and ways to minimize the exposed frontal area, but surviving the journey remains a major engineering problem. Arrival creates another limitation. A star chip would carry no practical braking system. It would enter the Proxima Centauri region at enormous speed and continue straight through. Instead of settling into orbit, it might have only hours for its closest observations before racing onward into interstellar space. Whatever information it collected would still need to reach us. A transmitter small enough for such a probe would have very limited power. Across more than 4 light-years, its signal would weaken enormously. Its high velocity would also shift transmitted frequencies through the Doppler effect, meaning motion changes the frequency received on Earth. Engineers would need exceptionally sensitive receivers and precise communication strategies. Even perfect success would therefore accomplish something narrower than human settlement. No passengers would travel aboard these probes. No food, habitat, machinery, or return vehicle could accompany them. Starshot is fundamentally a reconnaissance concept designed to obtain humanity's first close observations of another stellar system. Its timeline reinforces that distinction. A mature system would require years or decades of development before launch. Then comes roughly 20 years of flight, followed by more than 4 years for transmitted information to cross back to Earth. If you imagine the first returned images arriving sometime around the middle of this century, they would represent an extraordinary beginning. They would still be reconnaissance from a destination no human spacecraft can presently approach. Proxima b does not travel through an empty planetary system. Its orbit belongs to a neighborhood whose architecture is still being assembled from faint signals, long observations, and gravitational clues. That matters because planets influence one another over immense spans of time, even when their immediate paths appear orderly. In 2020, astronomers reported evidence for another possible world, Proxima Centauri c. The candidate follows a far wider orbit than Proxima b, taking roughly 1,900 Earth days to circle the star. Estimates place it somewhere in the broad territory between a super Earth and a smaller Neptune like planet. At that distance, it receives too little stellar energy for conventional liquid water at the surface. Then another signal appeared. In 2022, researchers announced Proxima Centauri d, a much smaller candidate orbiting inside Proxima b's path. Its year lasts only about 5 Earth days. If both outer and inner candidates are genuine, Proxima b occupies the middle of a compact system rather than circling Proxima Centauri alone. Multiple planets introduce gravitational interactions called perturbations, small changes in motion caused by neighboring bodies pulling on one another. Usually, these effects are subtle. Across millions or billions of years, however, repeated tugs can alter orbital shape, orientation, and timing. For habitability, those details matter. Long-term climate stability depends partly on receiving reasonably consistent energy from the host star. The larger stellar setting adds another influence. Proxima Centauri is associated with Alpha Centauri A and Alpha Centauri B, two sun-like stars bound together as a binary pair. Proxima lies extraordinarily far from them, at a separation on the order of 13,000 times Earth's distance from the Sunday. Their direct gravitational influence on Proxima b is therefore weak, yet the wider three-star architecture remains relevant over astronomical timescales. Researchers have modeled whether this arrangement threatens Proxima b's orbit. Studies generally find broad regions where the known or proposed planets can remain stable for very long periods. That is encouraging, but the calculation depends on quantities we have not measured precisely. Planetary masses, orbital inclinations, eccentricities, and even the status of some candidate worlds remain uncertain. This creates a subtle problem when we discuss a habitable zone. The term describes a range where stellar heating could permit surface liquid water under suitable atmospheric conditions. It does not guarantee that a planet stays within favorable conditions indefinitely. If gravitational interactions significantly changed Proxima b's orbit, its received energy could vary across geological time. So when you picture this nearby world, its position today tells only part of the story. We can estimate where Proxima b travels now and test plausible histories with computer models. Yet those histories depend on an incomplete planetary census. Until the system's architecture is measured more precisely, its long-term stability remains a modeled probability rather than a fully observed fact. A telescope nearly 1 million miles from Earth is helping us examine worlds whose light barely separates from their stars. The James Webb Space Telescope reached its operating region after launching on December 25, 2021. There, near the second Lagrange point, it observes primarily in infrared wavelengths, where distant planetary systems reveal details inaccessible to ordinary visible light observations. One of its most powerful techniques is transmission spectroscopy. When a planet crosses its star, from our perspective, some starlight passes through the planet's atmosphere. Molecules absorb particular wavelengths, leaving recognizable patterns within the spectrum. Water vapor, carbon dioxide, methane, and other gases can therefore reveal themselves without anyone directly sampling the atmosphere. For Proxima b, geometry creates a frustrating obstacle. The planet does not appear to transit Proxima Centauri from Earth's viewpoint. Its orbit carries it around the star without crossing the stellar disk as we see it. That prevents the James Webb Space Telescope from applying conventional transmission spectroscopy to Proxima b. Direct imaging offers another possibility. Instead of examining filtered starlight, astronomers try to separate the faint planetary signal from the overwhelming brightness nearby. Proxima b remains extremely difficult for the James Webb Space Telescope to resolve this way. Its small size and tiny apparent separation from Proxima Centauri place it beyond the telescope's practical direct imaging capability. Yet other red dwarf systems show what atmospheric observations can accomplish. TRAPPIST-1, about 40 light-years away, contains 7 roughly Earth-sized planets. In 2023, observations of TRAPPIST-1b found no evidence for a substantial atmosphere. Measurements of thermal emission indicated a world whose dayside radiates strongly, consistent with little atmospheric redistribution of heat. That result matters for our interpretation of Proxima b. TRAPPIST-1b circles an active red dwarf at extremely close range, creating another natural laboratory for understanding planets exposed to intense stellar environments. Still, the comparison has limits. Different planetary histories, magnetic properties, compositions, and stellar activity can produce different outcomes. One barren world cannot determine another world's condition. A future observatory could change what we know. The Habitable Worlds Observatory is a planned National Aeronautics and Space Administration concept intended to directly image potentially habitable planets around nearby stars. Unlike transit spectroscopy, direct imaging does not require a planet to cross its star from our viewpoint. Proxima b would be an exceptionally demanding target, however. Future instruments would need to suppress Proxima Centauri's light while isolating the much fainter planetary signal beside it. Spectroscopy could then search that separated light for atmospheric signatures. For now, you can see the boundary between discovery and characterization. We know Proxima b through its gravitational influence, while its atmosphere remains inaccessible to direct measurement. The James Webb Space Telescope has transformed studies of other exoplanets, but Proxima b's orbital geometry keeps its most important environmental properties beyond the telescope's strongest atmospheric technique. 7 rocky worlds orbit a star so small that their entire system would fit comfortably inside Mercury's path around the Sunday. This is TRAPPIST-1, about 40 light-years from Earth. 3 of its planets occupy or approach the region where temperatures could permit liquid water under suitable atmospheric conditions. That compact arrangement has made the system an extraordinary laboratory for testing ideas about red dwarf habitability. The James Webb Space Telescope has begun replacing some of those ideas with measurements. In 2023, observations of TRAPPIST-1b measured thermal radiation from its dayside. The temperature was roughly 450 degrees Fahrenheit. Such intense heating matched a world lacking a substantial atmosphere capable of carrying heat away from the star-facing hemisphere. TRAPPIST-1c offered another test. Observations published that same year found no evidence for the dense carbon dioxide atmosphere expected from a Venus-like world. The measurements instead favored either an extremely thin atmosphere or an exposed rocky surface. TRAPPIST-1c lies interior to the system's traditional habitable zone, yet its condition remains valuable because it reveals how atmospheres can evolve around an ultracool red dwarf. For researchers, these planets provide something Proxima b cannot yet provide: direct atmospheric constraints. Models have long predicted that close orbiting worlds around red dwarfs may struggle to preserve their gases. Now we can compare those calculations with actual planetary emission. The underlying difficulty begins early. Red dwarfs remain unusually luminous and magnetically active during their prolonged youth. Their planets form close to them, where high energy radiation can heat upper atmospheres and help gases escape into space. This vulnerable period may continue for hundreds of millions of years. Water can also be broken apart high in an atmosphere, allowing lightweight hydrogen to escape more readily. But the emerging evidence requires caution. TRAPPIST 1b and TRAPPIST 1c do not prove that every red dwarf planet loses its atmosphere. Several cooler TRAPPIST 1 worlds remain under investigation, and their atmospheric states are harder to determine. A substantial atmosphere has not yet been securely confirmed on an Earth-sized planet within a red dwarf habitable zone. That uncertainty changes how we interpret Proxima b. When its discovery was announced in 2016, its location within Proxima Centauri's habitable zone naturally attracted attention. Since then, atmospheric escape models and observations of comparable systems have made the picture more complicated. TRAPPIST-1 gives us measured examples of rocky planets exposed to red dwarf environments. Their apparent lack of thick atmospheres strengthens concerns that Proxima b may have experienced severe atmospheric erosion during its history. Yet you can also see where the evidence ends. We have examined only a small number of suitable worlds in meaningful detail. For now, these nearby red dwarf systems are teaching us that a favorable orbit alone says remarkably little about whether a planet can remain habitable. Mars carries its ancient climate in stone. Across crater walls, layered sediments, dried channels, and mineral deposits, the planet preserves evidence of conditions very different from those we see today. Between roughly 3.5 and 4 billion years ago, liquid water moved across parts of its surface beneath a thicker atmosphere. A global magnetic field once helped shield that environment from the solar wind. We can read parts of that history directly. The Curiosity rover has explored sedimentary rocks inside Gale Crater, where an ancient lake persisted through repeated environmental changes. Farther away, Perseverance entered Jezero Crater, whose western floor contains a remarkably preserved river delta. Sediments accumulated there roughly 3.5 billion years ago, carried by water into a lake that once occupied the basin. Minerals strengthened the geological record. Earlier missions discovered small hematite spheres, nicknamed blueberries, along with sulfate-rich layered rocks shaped by water-related chemistry. Clay minerals found elsewhere formed through prolonged interaction between rock and liquid water, sometimes under relatively mild chemical conditions. Together, these deposits show that ancient Mars supported lakes, rivers, groundwater systems, and environments capable of preserving organic material. Then the planet changed. Mars once possessed an internal dynamo, the process by which moving electrically conductive material inside a planet generates a global magnetic field. Evidence locked within ancient crust suggests that strong global magnetism disappeared very early, more than 4 billion years ago. Cooling inside the smaller planet likely weakened the dynamo, although the precise sequence remains under study. Without that broad magnetic protection, the upper atmosphere became increasingly exposed to charged particles from the sunday. Over immense spans of time, atmospheric gases escaped into space. Measurements from the Mars Atmosphere and Volatile Evolution mission have directly observed atmospheric loss occurring today, helping scientists reconstruct how a warmer, wetter planet became the cold desert we recognize. For human exploration, that history provides unusual clarity. Mars demonstrates the long-term consequences of atmospheric erosion, yet its surface remains accessible to machines and potentially manageable for protected crews. Its rocks contain water-bearing minerals, useful elements, ancient sediments, and a geological record we can physically sample. That record also gives Perseverance another purpose. The rover is collecting carefully selected rocks from environments where ancient microbial biosignatures could have survived. A biosignature is a chemical, mineral, or structural feature that may indicate past biological activity. Those samples are intended for detailed laboratory analysis if they can eventually be returned to Earth. If ancient life ever developed there, its traces may still remain inside sediments deposited when rivers entered Jezero's lake. You would then be looking at Mars as more than a difficult place for settlement. We would be studying a world that once possessed several ingredients associated with habitability, lost much of its protection, and still preserved the physical history of that transformation beneath our robotic explorers. A destination becomes materially different once governments begin budgeting for it, companies build hardware around it, and nations compete to reach it. Mars has crossed that threshold. Its exploration is no longer confined to scientific proposals. Rockets, surface systems, funding decisions, and national strategies now connect the planet to institutions operating on Earth. SpaceX demonstrated part of that infrastructure in October 2024 during Starship's fifth integrated flight test. The Super Heavy booster returned toward its launch site, where mechanical arms on the launch tower successfully caught it. Recovering such enormous hardware is central to rapid reusability, which could reduce the cost and turnaround time of launching large payloads. Government planning follows another path. The National Aeronautics and Space Administration's Artemis program is developing capabilities for sustained human operations around and on the moon. Lunar missions can test habitats, surface power, communications, resource use, and life support before comparable systems travel much farther. Mars therefore sits within an expanding technological chain rather than an isolated mission concept. Other nations have their own ambitions. China's Tianwen-1 mission delivered the Zhurong rover to Mars in 2021, making China the second nation to operate a rover successfully on the Martian surface. Chinese planners have also discussed future sample return and eventual human exploration. Mars increasingly belongs to a multinational landscape of scientific prestige and strategic competition. Economics complicates that landscape. Advocates describe off-world resource extraction, advanced manufacturing, and eventual settlements as foundations for entirely new industries. Asteroid resources are often included within this broader vision, yet trillion-dollar projections remain speculative. No functioning Martian economy exists, and early settlements would almost certainly consume enormous resources before producing meaningful economic returns. SpaceX has supplied the most aggressive public timelines. Elon Musk has repeatedly described near-term Starship missions to Mars, followed eventually by crewed flights. Schedules have shifted as development continues, but the important distinction is physical progress. Engines fire, vehicles launch, heat shields are tested. Recovery systems operate under real flight conditions. Political support remains less predictable. The Mars sample return campaign has faced major cost concerns, redesign efforts, and congressional scrutiny. Perseverance has already cached scientifically valuable samples, yet bringing them home requires sustained funding across many years. A technically possible mission can still slow when budgets change. Private investment now adds another source of momentum. Companies can finance launch vehicles, manufacturing facilities, communication systems, and spacecraft development alongside government programs. They still depend heavily on regulation, contracts, infrastructure, and public institutions, so independence has limits. When we compare destinations, this institutional machinery matters. Mars already occupies engineering schedules, national programs, industrial facilities, and government budgets. You can disagree about when humans will arrive while still pointing to hardware being built for increasingly ambitious missions. Proxima b occupies a fundamentally earlier stage, where scientific observation and exploratory concepts dominate because crude interstellar transportation has no comparable economic or technological infrastructure. Terraforming begins with an extraordinary premise that a planet itself could become part of the life support system. Instead of keeping people alive inside sealed environments, we would gradually alter the world around them. Atmosphere, temperature, pressure, and surface chemistry would all become engineering targets. On Mars, that idea has been studied seriously enough to reveal its limits. One familiar proposal begins with carbon dioxide. Mars stores carbon dioxide in polar deposits, minerals, and the shallow subsurface. Releasing those reserves could strengthen greenhouse warming and increase atmospheric pressure, yet the available inventory appears far too small. A 2018 analysis by Bruce Jakosky and Christopher Edwards concluded that accessible Martian carbon dioxide could not produce anything resembling Earth-like conditions. Even mobilizing known reservoirs would leave atmospheric pressure far below what humans require. There is another obstacle above the atmosphere. Mars no longer possesses a strong global magnetic field. Solar wind therefore interacts directly with its upper atmosphere, allowing particles to escape into space. Any artificially thickened atmosphere would face this continuing loss over long timescales. Restoring a planetary magnetic dynamo would require manipulating processes deep within Mars, something far beyond existing engineering. So terraforming becomes a spectrum rather than one transformation. Full planetary conversion remains inaccessible, while smaller environmental changes are easier to imagine. Pressurized greenhouses could maintain warmer temperatures, richer air, and controlled water cycles. Large, enclosed settlements might eventually create regional environments where plants grow without individual pressure suits. We already understand many of the underlying technologies, even if deploying them across Mars would require generations. Outside those structures, conditions would remain Martian. Early settlers would still depend on pressure walls, airlocks, radiation protection, and manufactured oxygen. Any broader transformation would likely unfold across centuries or millennia. The people beginning such a project might never witness its intended outcome. Biology offers another possibility. Researchers have discussed engineered microorganisms capable of fixing nitrogen, producing oxygen, or altering minerals. Such organisms could potentially assist closed agricultural systems and, in more speculative scenarios, participate in gradual planetary modification. But biological terraforming introduces an ethical problem before an engineering one. What if native Martian microbes still survive underground? Introducing terrestrial organisms could contaminate ecosystems we have barely begun searching for. You would then face a question without a purely technical answer. Does making another world useful to humanity justify permanently changing its independent biological history? That question becomes even harder around Proxima Centauri. Before discussing terraforming Proxima b, we would need to know whether it has a solid surface, an atmosphere, accessible water, and conditions allowing those resources to persist. We currently lack those foundations. Mars gives us measurable constraints, physical materials, and testable engineering problems. Terraforming remains immensely difficult there, but at least we know what world we are proposing to change. Imagine arriving somewhere that can never receive help from home. Even under the most favorable assumptions, Survival on Proxima b begins there. We would have to assume a rocky surface, accessible water ice, and an atmosphere substantial enough to offer some protection. None of those conditions is confirmed. Yet granting all three still leaves a settlement facing requirements unlike anything humans have attempted. Radiation would shape almost every structure. Proxima Centauri produces powerful stellar flares, including events energetic enough to bombard a nearby planet with intense X rays and ultraviolet radiation. Habitats would need shielding capable of protecting residents repeatedly, perhaps through thick layers of local rock or deeply buried construction. Surface activity would require additional protection. Current materials cannot make prolonged exposure during extreme flare conditions routinely safe at planetary scale. Energy presents another constraint. Large solar installations could suffer damage during severe stellar activity, while changing radiation conditions would complicate dependable surface operations. Nuclear systems therefore become attractive because they can operate independently of starlight. But we know nothing about accessible nuclear fuel deposits on Proxima b. An initial settlement would need to carry fuel, reactors, replacement components, and the machinery required to maintain them. Then distance changes the meaning of communication itself. Proxima b lies about 4.24 light years away. A message sent toward Earth would require roughly 4.24 years to arrive. Any response would return after another 4.24 years. A simple exchange could therefore span about 8.5 years. Mission control could provide knowledge, but never immediate assistance. Physical resupply is more severe. With propulsion comparable to our fastest practical spacecraft, transporting substantial cargo across interstellar space would require thousands of years. Medicine cannot arrive next month. A failed pump cannot be replaced next year. Food shortages cannot trigger an emergency shipment. Every critical system would need redundancy, repairability, and local manufacturing from the beginning. That permanence reaches beyond engineering. The founding population would carry only part of humanity's genetic diversity. Over many generations, genetic drift and inbreeding could become serious concerns unless reproductive planning and preserved genetic material maintained sufficient variation. Such systems would have to endure for centuries without replenishment from Earth. Culture would separate as well. Children born there could never expect to visit humanity's birthplace. Their descendants would inherit languages, institutions, technologies, and traditions increasingly shaped by another star. Earth would remain visible through messages arriving years after the lives that produced them had already changed. So, what does survival really require? A Proxima b settlement would need dependable shielding, autonomous power, closed food and water cycles, advanced medicine, local industry, genetic planning, and social institutions capable of functioning indefinitely. Every essential system would need backups and repair pathways. On Mars, failure can still leave some possibility of outside intervention. On Proxima b, the first settlers would have to arrive already prepared to become an independent civilization. A galaxy filled with stars should offer countless opportunities for life. Yet when we listen, search, and examine nearby worlds, we find no confirmed civilization beyond Earth. This tension is known as the Fermi paradox. If intelligent life can arise elsewhere, where is everyone? Where are the signals, artifacts, probes, or other traces that an ancient technological species might leave behind? One possible answer is the rare Earth hypothesis. It proposes that simple life may arise fairly often, while complex organisms require an unusually narrow combination of conditions. A stable star matters. So do long-lasting surface water, atmospheric protection, suitable chemistry, and geological stability. Magnetic shielding may help preserve an atmosphere. Even planetary neighbors and large moons could influence climate and orbital evolution. Proxima b gives this debate an unusually nearby example. It occupies a region where temperatures might permit liquid water under certain atmospheric conditions. Yet its red dwarf star produces powerful radiation and frequent flares. We still cannot confirm whether the planet possesses an atmosphere, oceans, or a protective magnetic field. Its proximity, therefore, teaches us something important. Being located within a habitable zone does not guarantee habitability. That distinction becomes significant across the galaxy. Roughly 70% of Milky Way stars are red dwarfs. Their small size and long lifetimes once made them promising hosts for life. But their planets orbit close enough to experience intense stellar activity, particularly during the star's energetic youth. If atmospheric erosion commonly leaves those worlds exposed, an enormous fraction of apparently promising planets may prove hostile to complex biology. Location within the Milky Way may matter too. Researchers have proposed a galactic habitable zone, a broad region where conditions could favor rocky planets and biological evolution. Too near the galactic center, stellar crowding and energetic events may increase environmental hazards. Farther outward, lower concentrations of heavy elements could historically reduce the raw materials available for building rocky worlds. Suppose complex life really is rare. The absence of detectable civilizations becomes easier to understand. Earth may represent an uncommon convergence of planetary stability, chemistry, time, and favorable astronomical circumstances. Life itself could be widespread, while technological intelligence remains exceedingly scarce. But suppose complex life is common, then the puzzle becomes deeper. Civilizations could exist while remaining separated by distances so immense that meaningful contact rarely occurs. Signals weaken, travel consumes extraordinary time and energy. Entire cultures could rise and disappear before information crossed the space between them. Proxima b cannot resolve the Fermi paradox. No single planet could. What it does provide is a nearby reminder that promising labels can conceal severe physical constraints. When we consider Mars from that perspective, its importance changes. Reaching another world becomes more than exploration. It becomes an experiment in whether intelligence can extend life beyond the one environment where we know, with certainty, that it succeeded. A civilization confined to one planet carries a simple vulnerability. Every archive, city, laboratory, language, and living human remains inside the same planetary system of risk. Most disasters would not erase our species. A sufficiently extreme event, however, could threaten civilization globally, and some natural hazards reveal how large those events can become. 66 million years ago, an asteroid roughly 6 miles wide struck near the present-day Yucatan Peninsula. The impact formed the Chicxulub crater and helped trigger the Cretaceous Paleogene extinction. About 75% of species disappeared, including every known avian dinosaur lineage. Earth recovered biologically, but the process unfolded across immense spans of time. Volcanism offers a different scale of disruption. Yellowstone has produced enormous eruptions during its geological history, including one roughly 630,000 years ago. Another eruption of comparable magnitude could spread ash across broad regions and severely disrupt agriculture and transportation. Yet Yellowstone is closely monitored, and scientists do not consider a supereruption imminent. Mars enters this discussion through risk distribution. A genuinely independent settlement there could preserve human populations, knowledge, technology, and culture if Earth suffered a global catastrophe. SpaceX has explicitly presented making humanity multiplanetary as a central reason for pursuing Mars. The National Aeronautics and Space Administration approaches Mars differently, emphasizing exploration, science, technology development, and preparing humans for increasingly distant missions. The crucial word is independent. A small outpost receiving regular shipments from Earth would provide little insurance during a planetary emergency. A true backup population would need its own food production, medicine, energy, manufacturing, governance, education, and capacity to replace complex machinery. How many people would that require? There is no accepted minimum. Population studies produce very different answers, depending on assumptions about genetics, stored reproductive material, technology, specialization, and social organization. Some models suggest surprisingly small founding populations could remain genetically viable under carefully managed conditions. A technologically self sustaining civilization would likely demand far more people. Elon Musk has repeatedly discussed an eventual Martian population around 1 million as a scale capable of supporting independence. This is where distance changes the comparison completely. Mars can be reached within months during favorable opportunities. A settlement established there could exist during crises occurring within the lives of people already born on Earth. Proxima b cannot occupy that role. With present propulsion, meaningful human transport across more than 4 light years would take thousands of years, and the destination itself remains poorly characterized. So the comparison is larger than comfort or surface conditions. You can imagine Mars becoming another inhabited branch of humanity while maintaining contact with Earth during its development. Civilizational insurance only begins to function when that branch can survive the loss of its origin. Mars presents a conceivable path toward that threshold. Proxima b, for any planning horizon we can responsibly describe today, does not. The landing would begin before anyone on Earth could help. A crewed spacecraft approaching Mars would enter an atmosphere less than 1% as dense as Earth's at the surface. That air is thick enough to create dangerous heating, yet too thin to provide easy braking. Heat shields, aerodynamic drag, parachutes, and retro rocket engines would have to work in sequence. During those minutes, the crew would depend entirely on systems already aboard. Mars would make the separation from Earth immediately tangible. Depending on the planet's positions, radio messages take roughly 3 to 22 minutes to travel one way. Mission Control could receive confirmation only after events had already happened. By the time Earth learned that the spacecraft had landed, the crew might have spent many minutes standing safely on another world. Outside, the familiar photographs would become a surrounding landscape. Iron oxide dust gives much of the terrain its reddish-brown color. Fine particles suspended overhead often make the daytime sky appear tan or salmon-colored. The sun would look smaller than it does from Earth, casting light across rocks shaped by impacts, ancient water, wind, and immense geological time. Near sunset, Mars reverses an earthly expectation. Fine atmospheric dust scatters light so that the region around the setting sun can appear blue. The Spirit rover recorded such a sunset in 2005. For a human crew, that blue glow would arrive through helmet visors and habitat windows rather than camera images transmitted across space. Sound would behave differently too. Mars has an extremely thin atmosphere dominated by carbon dioxide. Experiments using the Perseverance rover's microphones showed that sound travels more slowly there than on Earth, and higher frequencies fade rapidly. Outside a pressurized habitat, astronauts would communicate through radio systems inside their suits. The environment beyond them would carry sound only weakly. Time, however, would feel surprisingly familiar. One Martian solar day, called a sol, lasts about 24 hours and 39 minutes. Human sleep schedules could therefore follow a cycle close to Earth's, unlike environments with radically different day lengths. You could wake, work, eat, and sleep according to a rhythm our biology already recognizes. Then there would be Earth itself. From Mars, our planet can appear as a bright point in the sky, sometimes accompanied visually by the moon. Cameras aboard Martian spacecraft have already photographed that distant pairing. For the first settlers, the point would also function as a direction. Every delayed message, family recording, technical instruction, and remembered place would originate there. You could raise your eyes above the Martian horizon and locate the world where every human generation before yours had lived. From that surface, Earth would no longer fill the sky of experience. It would occupy a tiny piece of it. 23 sealed pieces of Mars now wait inside sample tubes on another world. Perseverance collected them across Jezero Crater, drilling sedimentary rocks formed when water occupied the basin billions of years ago. Those rocks preserve layers where chemistry once unfolded in an environment capable of supporting microorganisms. For astrobiology, they are among the most valuable materials ever collected beyond Earth. Returning them has proven difficult. The Mars Sample Return Campaign, developed through the National Aeronautics and Space Administration and European Space Agency, was designed to transport selected tubes back to Earth. Cost increases and technical complexity have forced major revisions to that architecture. Yet the scientific objective remains powerful because laboratories on Earth can perform analyses far beyond anything a rover can carry. Scientists would search at several scales. Complex organic molecules could preserve traces of ancient carbon chemistry. Isotopic ratios, meaning the relative amounts of different forms of an element, might reveal patterns associated with biological activity. Microscopic structures could provide another line of evidence. Researchers would especially examine possible microfossils and layered formations resembling stromatolites, structures that microbial communities produced on ancient Earth. Any sample would require extraordinary containment. Scientists must protect Earth from unknown Martian material while protecting the samples from terrestrial contamination. Even ordinary microbes introduced during analysis could confuse results. Evidence for another biology demands multiple independent measurements before anyone could responsibly claim discovery. Mars also presents a mystery still unfolding above its rocks. The Curiosity rover has detected changing methane concentrations near Gale Crater. Methane can arise through several pathways, including geological reactions involving rock and water. Biology can produce it too. Ultraviolet radiation and atmospheric chemistry eventually destroy methane, so measurable releases suggest some source is replenishing it. Yet the picture remains complicated. Measurements from orbit have not always matched detections made at the surface. Local geology, atmospheric circulation, seasonal changes, or unknown chemical processes could explain part of that disagreement. We therefore cannot treat methane as evidence of organisms. Its source remains unresolved. Suppose returned rocks eventually contained convincing ancient biosignatures. We would then have evidence that biology emerged somewhere beyond Earth, whether independently or through material exchanged between the planets. Determining which possibility occurred would become another major scientific problem. Even so, a second biological record within our solar system would transform estimates of how readily life begins. A barren result would matter too. If environments containing long lived water and useful chemistry never produced life, then habitability alone may be insufficient. You could have the ingredients, the setting, and immense spans of time without biology appearing. That is why Jezero Crater carries such scientific importance. Mars preserves a planetary experiment whose conditions unfolded billions of years ago. We have reached the ancient sediments, drilled into them, and sealed pieces away. Somewhere inside those rocks may be evidence that changes our estimate of life's place in the universe, or evidence that makes Earth's living history appear far less common. Beyond the nearest star, distance rapidly becomes the dominant filter. A promising planet can satisfy several conditions for habitability and still remain beyond meaningful human access. So, when we ask which worlds deserve attention, two different questions emerge. Which planets might support life, and which could humanity realistically reach? The TRAPPIST 1 system remains scientifically valuable. At roughly 39 light years away, it contains 7 known rocky planets, including several near the star's habitable zone. Among them, TRAPPIST 1e has often received particular attention because its size, density, and incoming stellar energy make it an intriguing terrestrial candidate. Yet, its red dwarf host brings familiar concerns. Observations by the James Webb Space Telescope are testing whether planets in this system can retain substantial atmospheres under intense stellar activity. A different possibility lies much farther away. Kepler 452 b was announced in 2015, orbiting a star broadly similar to the Sunday. Its year lasts roughly 385 Earth days. The planet's estimated radius is around 1.6 times Earth's, although its mass and composition remain uncertain. At about 1400 light years away, however, Kepler 452b belongs to astronomy rather than practical exploration. Even extraordinary future propulsion would leave that gulf immense. Closer to home, Tau Ceti has attracted attention for decades. The star lies around 12 light years away and resembles the Sun more closely than Proxima Centauri does. Candidate planets have been reported there, including Tau Ceti e, often modeled as substantially more massive than Earth. Its exact habitability remains uncertain because orbital properties, atmospheric conditions, and even some planet detections require further confirmation. These examples reveal what astronomers would prefer to find nearby. An especially compelling target would be rocky, roughly Earth mass, and orbiting within the temperate region of a stable star. A star somewhat cooler than the Sun could be particularly useful because such stars can remain stable for very long periods. A detectable atmosphere would strengthen the case further. Evidence for surface water would transform it. We have not yet confirmed that complete combination within 30 light years, and distance remains unforgiving. Even a destination 10 light years away would challenge propulsion concepts far beyond today's crude spacecraft. Generation ships, advanced fusion propulsion, or other technologies might someday alter the calculation, but none presently offers a demonstrated path for transporting people between stars. That leaves a striking difference between discovery and settlement. During the next several centuries, telescopes may identify worlds far more Earth-like than Mars. We may even detect atmospheric chemistry, suggesting biology, but knowing that a better world exists does not make it reachable. Mars occupies another category. It is difficult, hazardous, and profoundly unlike Earth, yet spacecraft already cross the distance. We can land machines there, study its soil, map its resources, and design human missions using technologies rooted in present engineering. The stars remain destinations for a more distant civilization. Mars belongs to ours. Some of humanity's longest projects began with builders who knew they would never see completion. Medieval cathedrals could take generations to finish. Stonecutters shaped walls for roofs their grandchildren might someday stand beneath. The work mattered because its value extended beyond a single lifetime. A settlement on Mars would demand similar thinking. The first crews could establish habitats, power systems, laboratories, and resource processing. They would still depend heavily on Earth. Later generations might expand underground living spaces, agriculture, manufacturing, and local industry until fewer supplies had to cross interplanetary space. True self-sufficiency could require centuries. Those founders would begin something larger than themselves. We already have machines demonstrating how human work can outlive its creators. Voyager 1 left Earth in 1977. Decades later, it had traveled more than 15 billion miles, carrying instruments built by engineers from another technological era. Its journey became longer than many human lives. The spacecraft reminds us that carefully built things can continue serving purposes long after their designers leave the story. Mars asks us to extend that principle towards civilization itself. Does humanity have an obligation to preserve its future? We cannot answer that with engineering alone. We are the only confirmed technological species known anywhere in the observable universe. Every scientific theory, painting, language, memory, and recorded history we possess currently depends upon one inhabited planet. That concentration creates vulnerability. A catastrophe severe enough to end civilization could erase far more than the people alive during it. Thousands of years of accumulated knowledge could disappear with them. So could countless futures that never received the opportunity to exist. A permanent settlement elsewhere would change that equation. Mars would remain harsh, dependent on technology, and difficult to develop. Yet, a sufficiently mature population could preserve human knowledge and culture even if Earth experienced a global disaster. Building such resilience would require generations who accept benefits they may never personally receive. Children living today occupy an unusual point in history. Human footprints on Mars could plausibly occur within their lifetimes. Whether settlements follow would depend on politics, economics, engineering, public commitment, and the willingness to sustain projects beyond election cycles and individual careers. Proxima b belongs to a different scale of time. It will continue orbiting its star centuries from now, waiting for technologies capable of making interstellar travel practical. There is no comparable urgency to reach it. Mars is different because the necessary foundations already exist. We can send spacecraft there. We understand much of the environment. Hardware for deeper human exploration is being developed now. What happens with that capability becomes a choice passed from one generation to another. The people who begin a permanent human presence on Mars may never witness what it eventually becomes. Like builders laying foundations centuries ago, they would create something intended for people whose names they could never know. On February 14th, 1990, Voyager 1 performed an unusual maneuver. Nearly 3.7 billion miles from Earth, the spacecraft turned its camera toward the worlds it had left behind. Among the resulting images was Earth, occupying less than a single pixel within scattered sunlight. Almost everything humans had ever experienced existed inside that speck. Carl Sagan later gave the image its enduring name, the pale blue dot. Its scale became even more meaningful as our knowledge of other worlds expanded. We now know that planets are abundant, yet abundance does not guarantee another Earth nearby. Proxima b makes that distinction especially clear. Roughly 4.24 light-years away, it occupies a region where temperatures could permit liquid water under suitable atmospheric conditions. But its red dwarf star exposes the planet to intense stellar activity. Whether Proxima b possesses an atmosphere remains unknown. The nearest potentially temperate world may therefore be profoundly hostile. Mars gives us another comparison. Its surface records what can happen when planetary protection weakens across geological time. Earth currently retains a strong global magnetic field and an atmosphere containing an ozone layer that absorbs much harmful ultraviolet radiation. These systems emerged from planetary processes operating over billions of years. They are part of the physical architecture that allows our surface environment to remain habitable. Astronauts who see Earth from orbit sometimes describe a lasting change in perspective. Researchers call this the overview effect, a shift associated with viewing Earth as one interconnected planetary system. National borders disappear from that altitude. Oceans, clouds, continents, and atmosphere become features of a single world moving through space. That world also has a finite future. The Sun is a middle-aged star whose luminosity gradually increases. Models suggest that within roughly 1 billion years, increasing solar energy could make Earth increasingly hostile to surface oceans. Around 5 billion years from now, the Sun will evolve into a red giant, radically transforming the inner solar system. Cosmic time is generous, but not infinite. Mars can approach within roughly 34 million miles of Earth. Proxima Centauri remains more than 4 light-years away. Those distances belong to entirely different categories of travel. One can be crossed by spacecraft using technologies we already understand. The other demands capabilities humanity has yet to demonstrate. Still, we have always looked beyond immediate reach. Ancient cultures named stars they could never visit. Modern engineers sent Voyager spacecraft outward carrying golden records with sounds and images from Earth. We preserve knowledge because someone may need it later. We explore because distance has never erased curiosity. From Voyager's perspective, Earth was almost nothing in the frame, yet that tiny point contained oceans, forests, cities, music, memory, and every person who had ever looked upward. Mars does not replace that world. It extends the reach of the life that began here. One day, human eyes may look back from its surface toward the same pale blue point, carrying Earth's story farther than it has ever gone.